for that part of the exam. So the Blackboard exam, open book, open note, but we will all be on WebEx. And then the learning assessment, though, all you can have is that one note card. That's it. Just the one note card, whatever you'd like to put on it, but that one note card. Okay? You're welcome. All right. Any questions before we begin chapter 13? All right, so here we are going to talk about a new functional group, but before we get into that, let's look at Ecclesiastes 12. It says, honor and enjoy your Creator while you are still young, before the years take their toll and your vigor wanes, before your vision blurs and the winter years keep you close to the fire. So make sure that even now you're saying, let me go to the Creator, let me honor Him, and let me enjoy Him, enjoy the Creator while you're still young. Don't wait until you're on your deathbed and say, okay, now I knew what I should have done. Now I'm going to say, oh, God, forgive me, blah, blah, blah. No, honor and enjoy Him now. Let yourself have a good life in the presence of God. I'm not saying everything will be perfect in the presence of God, but I'm saying He will give you a good life because He's a good God with good plans. It might not be your plans, but He has good plans for you. So honor and enjoy Him now while you are, young and you have all these years ahead of you. All right, so let's look at our alkynes. So our alkynes are going to be, right, the carbon-carbon triple bond. Our simplest alkyne, the smallest one, is just two carbons with a triple bond between them. That has a common name, acetylene. Have you heard of an acetylene torch? This is the compound that is in that. But that's just a common name. It has an IUPAC name. The IUPAC name is ethyne. So what did we do before? We have our prefix, and then we put Y-N-E on the end to say that this is an alkyne. We don't need a number there when it's just two carbons. We don't even need a number really when it's three carbons. We need numbers when it's four or more to say where this alkyne is. So here is the alkyne between carbons 1 and 2, or between 3 and 4. Here it's between 2 and 3. So this is 2-butyne. And I could have numbered that the opposite direction. It didn't matter which direction. Whenever we have an alkyne, though, we want to number the carbon chain to get to the alkyne as quickly as possible, if that is the longest carbon chain. So think about the same rules we had back with the alkenes, right? What did we say with the alkenes? We look for the longest carbon chain. If our longest carbon chain includes the unsaturation, so the alkene or the alkyne, then we need to number it from the end that gets us to the alkyne or the alkene as quickly as possible. If our longest carbon chain doesn't include it, then we name the alkyne as a substituent, which we will talk about on the next slide. So here the longest carbon chain is 6 carbon, so hex. It does include the alkyne, so hexyne. And with this, we number it from the left to get to the alkyne as quickly as possible. So it's on carbon 2, so 2 hexyne. And then on carbon 4, we have the bromo. This is what we would call an internal alkyne. Internal alkyne meaning that there's a carbon on either side of the 2 carbons of the alkyne. So this is also an internal alkyne. This is technically terminal, but there's not really anything else on this, but this would be a terminal alkyne. Here we have another terminal alkyne where we only have a hydrogen on the other side of that one of those carbons of the alkyne. We number it the longest carbon chain. Here it is 4 carbons long with the alkyne. So where is the alkyne? It's between carbons 1 and 2, so 1-butyne, and then 3,3-dimethyl for the other 2 groups that we have there. So again, number your longest carbon chain. If your longest carbon chain includes the alkyne, name it as an alkyne. If your longest carbon chain does not include the alkyne, name it as an alkane, and your alkyne is a substituent. So how do we name the alkyne as a substituent? We call it an alkynyl group. An alkynyl group. So here we have a 6-membered ring, so cyclohexane, and with that we have 2 groups. So 1, 2, 1, 2. 2 of these 2 carbon alkynes. So what do we call them? Ethynyl, but we have 2 of them. So diethynyl. Where are they? On carbon 1, on carbon 2, of this 6-membered ring. So 1,2-diethynyl cyclohexane. Here, there's some stereochemistry shown, so we could put trans, or, we could do RS instead. Trans or RS. So remember, RS would be better. So this 2-carbon substituent, we call that ethynyl. If we have 3 carbons, so here we have a cyclobutane, 4-membered ring, coming off of carbon 1. We only have one thing attached, so notice that there's no number here. No number. So we don't have a number here in front of the cyclobutane. We don't have a number here. There's no parentheses. Here we're just calling this 2-propynyl. So no parentheses. So I'm putting parentheses and I'm crossing them off. No number in the front. No number here. Because we don't have to say that this is carbon 1. Right? So we do not need to say that that's carbon 1. So let me erase all that so that we can see this a bit clearer. So here, what do we need to say? Well, we need to say that this 2 now is referring to where the triple bond is. The triple bond is between carbons 2 and 3. So that's what this 2 is for. 2-propynyl. Because we could also have 1-propynyl. Where now we have the triple bond here between 1 and 2, rather than between 2 and 3. So we put our triple bond between 1 and 2, this would be 1-propynyl cyclobutane. Now, this is a complex substituent, so you will have to put it into parentheses if we have more than one thing. But again, we don't put a number in the front. We don't need parentheses here just because we only have this one group. But we can have more things happening. So if I gave you this, so here we have a methyl. Here we have 1, 2, 3. We'll add on a 4th carbon just to make it different. So we have 4 carbons now for our alkyne. What's the name of this? Well, this substituent would be called 2. And then here we have 4 carbons, so bute, ine, ol. Butine, and then YL saying it's a substituent. Which one comes first alphabetically? M versus B. B comes first, so this is on carbon 1, this is on carbon 2. So this would be 1 dash parentheses now. Now we need parentheses because we have more than one thing, and this is a complex substituent. 2-butynyl, and then 2-methyl cyclohexane. So then let's look at our last example here. So I've just shown you rings. So if it's attached to a ring, you know it's a substituent. Here, when it is a straight chain, our longest carbon chain does not include the alkyne carbons. Our longest carbon chain is just 9 carbons long. And so on carbon 4, we have this ethynyl group. It's a 9-carbon chain, nonane. And then we see that this is a chiral carbon. And so we have to say, is this R or is this S? We add that into the beginning of the name. Questions here? And then the last thing I forgot to say is that this is called propargyl. That's the common name for this group where it is a 2-propynyl. That is called a propargyl group.
Dr. Nalbandian?
Mm-hmm.
So would the EZ method for naming just be for alkenes then?
Mm-hmm.
Okay.
Because this is linear, we can't do EZ with alkynes. We can't do cis trans with alkynes. The trans that you see here isn't about the alkyne stereochemistry. It's about, you know, this being a wedge, this being a dash. That's where you're seeing trans there. So that was the RS kind of trans, not the EZ kind of trans with the alkenes. But we can have alkenes and alkynes in the same molecule. We can have both alkenes and alkynes. So we name them as alkene ines. Alkene ines. So if that is the longest carbon chain, your longest carbon chain here is your longest carbon chain. If your longest carbon chain includes both an alkene and an alkyne, then you name it as an alkene ine. If it doesn't, then you name it maybe as an alkene with an alkyne substituent, or if it contains the alkyne with an alkene substituent, or whatever. Look for your longest carbon chain, figure out what your substituents are. But here we're talking about if your longest carbon chain includes both a double bond and a triple bond in it, we call it an alkene ine. So for an alkene ine, you're going to number from whichever end gets you to the alkene or the alkyne as quickly as possible. Either one, whichever one you get to first. If you have a tie, then the alkene gets the lowest number. So let's look at this first one. This first one, we have 6 carbons. Which end do we number from? We number it from this end because it gets us to an alkyne as quickly as possible. Either the alkene or the alkyne as quickly as possible. We get to the alkyne as quickly as possible. So this would be 3-hexene 1-ine. 3, because carbon 3, between 3 and 4 we have the hexene, and between carbon 1 and 2 we have the ine. So 3-hexene 1-ine. Or we could write hex 3-ene 1-ine. Remember, we're dropping the E on the end here for the alkene, but we are going to keep the E on the end for the alkyne. Here we have a tie. 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, the numbering that you see on the top or on the bottom. Which one is correct? Well, we have a tie here, so the alkene gets the lowest number, only when you have a tie. So this is called 1-pentene 4-ine, or pent 1-ene 4-ine. Either one is fine. So what happens if we add in a hydroxy group? We can add in a hydroxy group to an enine, but here they're only showing you a hydroxy group added into an alkyne. So you know that more bonds to oxygen, higher priority group. So this is a higher priority group, the hydroxy group. So whenever we add an alcohol, the longest chain has to include the alcohol. Your longest chain has to include the alcohol if there's one there, as long as there's nothing higher priority there. And so with the alcohol, if that's your highest priority group, you number it to get to that as quickly as possible. It doesn't matter that this could be carbon 1 with the alkyne. You're numbering it this way because we need to get to the alcohol as quickly as possible. So the alcohol here is on carbon 2, 3, 4, 5, 6. So this is 5-hexyne 2-ol, or hex 5-ine 2-ol. Notice that we're dropping the E for the alkyne, and we're ending it with ol. Then our last one here, again, number it to get to the alcohol as quickly as possible. So this is carbon 1. We have an alkyne between carbons 2 and 3, so 2-propyne 1-ol. Even though this is a 3-carbon chain, we have to say where the alkyne is now because we've added an alcohol. If this was just a regular 3-carbon alkyne, then we would just call this propyne. No number needed, just call it propyne, because there's only one way to do it. It has to be between carbons 1 and 2. But now that we have the alcohol, is the alkyne between 1 and 2, or is the alkyne between 2 and 3? We have to specify, and so we put 2 in front of propyne, 1 in front of ol, This has a common name, propargyl alcohol, based on what we saw before. Now, the last thing here is they didn't show you anything, but this alkene, it's 1,2 disubstituted, so you could do cis-trans, or you could do EZ here for this alkene, right? It's 1,2 disubstituted. Here, this is mono substituted, so we can't do cis-trans EZ for this. But remember, whenever we have an alkene, any kind of alkene, remember we have to look for, okay, can we do cis-trans? Can we do EZ? We have to look at that. They're not showing you that stereochemistry as they've drawn it, but if they drew it, you know, like this, then you have to specify. But as they're drawing it in the condensed form, they're not showing you that, but just keep that in mind. Questions on any of the nomenclature stuff? All right, let's look at our properties of the alkynes. So what do we know about the type of bond, right? We have alkane. We said alkane is made from a sigma bond. We have alkene. We said alkene is sigma plus pi. And so then what is an alkyne? Sigma plus pi plus pi. 2 pi bonds for an alkyne. 2 pi bonds for an alkyne. All right, so looking at the boiling points for alkynes, alkenes, alkanes, all very similar. They all have just the London dispersion forces. They're all mostly nonpolar, and so they have about the same boiling points. So when we look at our carbon-carbon triple bond, we'll just make it the simplest alkyne. Each carbon is sp hybridized. Each carbon is sp hybridized. So what does that look like? Well, let's go back to basics. Oops. So we have a carbon atom. We know a carbon atom is 1s, has 2 electrons in it, 2s, 2 electrons, and then 2p, 2 electrons. If we want to make bonds, we want to make 4 bonds, so we have to promote 1 electron in order to make 4 bonds. So nothing happens to our 1s, nothing happens to our 2s, nothing happens to our 2p orbitals, but now we just have 4 electrons that are unpaired so that we can make 4 bonds. From here, this is what we start off with to hybridize. So we did the same thing when we were doing sp3, sp2, and now we're doing it for sp. So how many s orbitals, how many p orbitals do we need in order to make sp? It's 1 part s and 1 part p. It's sp, 1 part s and 1 part p. Nothing happens to 1s, and nothing happens to these other 2p orbitals. Nothing happened. Keep those the same. If we mix 2 orbitals, we need to make 2 orbitals. Mix 2, make 2. What are these 2 new orbitals called? sp. 1 part s, 1 part p. How many electrons did we have? Well, we had 1 and we had 2, so we need to still have 2. Each of our carbons here has this electron configuration. So this carbon has that electron configuration, 2 of these sp orbitals, and then 2 of these 2p orbitals, and this carbon has the same thing. So with that in mind, what are we looking at here for a carbon? Well, the carbon, as I said, each carbon, so look at this on the left, each carbon has 2 of these sp orbitals. I'm going to call this, we'll call this A, B, we'll We'll call this X and Y. So where is A coming in? This is A, and then where is B? This is B. So remember what an sp orbital looks like. It has one large lobe, and then it has a smaller lobe. So you can see the smaller lobe right here. You can see they're showing you the small lobe. So we're looking at the large lobe. I put A on the large lobe. I put B on the large part of the lobe. But this here is A's small lobe. And over here you can see B's small lobe, the small lobe of it. So we have these two sp orbitals. And then remember what a p orbital looks like. A p orbital is the same size on both ends. So what do we have here? For our p orbital, X, this is the top and bottom of X. This is the front and back of Y. So remember how these orbitals look. X is going to be here, straight up and down, and Y is going to be pointed towards you, away from you and towards you. That's what Y is. So these two orbitals are perpendicular to each other. We have two perpendicular 2p orbitals. They are going to overlap to give us these two perpendicular pi bonds. So where are our pi bonds? Well, here, each carbon is bringing these 2p orbitals. So here we get this pi bond with this overlap above and below. And then here, these ones that are pointed toward us, so in the front and the back, that overlap. Remember, we get this overlap like this. This is a pi bond. Top and bottom overlap, that's a pi bond, but side to side. So we have two pi bonds that we're forming here. What did we say an alkyne is? In the middle of that alkyne, it's a sigma plus a pi plus a pi. Where are these pi bonds coming from? These 2p orbitals overlapping above the plane and below the plane. That gives us one pi bond. And then the other 2p orbital here in front and in the back overlapping, that's giving us our second pi bond. So you can see a pi bond here. They're drawing arrows to the two different kinds of pi bonds here on this structure. Let me erase my lines here. So we can see our pi bonds. So those green lines are showing you the different pi bonds, and you see we have two pi bonds. Well, what about our sigma bond? Remember, sigma bonds are face-to-face overlap, not side-to-side. They're face-to-face overlap. And to make sigma bonds, we use hybrid orbitals, right? Hybridized orbitals. To make pi bonds, we use 2p orbitals, unhybridized 2p orbitals. So here is our sigma bond here in the middle, where one carbon's sp and another carbon's sp overlap. Each carbon has an sp orbital. Those are overlapping to give us a sigma bond. And then we said we have one sp orbital, so one sp orbital from one carbon, an sp orbital from the second carbon, but we have to make a bond on the other side. What we're looking at here is a triple bond between these two carbons, and then a single bond between carbon and hydrogen. So we need another sigma bond here. That is a sigma bond. A single bond is a sigma bond. And so we get this overlap here between the sp orbital of carbon and the 1s orbital of hydrogen. Those are overlapping face to face, and so we make another sigma bond. So this is that sigma bond here. What are we making in here? What's in here? Well, there's us, one sigma, and then we have two pi bonds to make that triple bond. And then here on this side, that is another sigma bond between carbon and hydrogen. So we have this triple bond between these two carbons, With the triple bond, to make the triple bond, we're using one sp orbital to make a sigma bond, one 2p orbital to make a pi bond, and another 2p orbital to make a pi bond. Each carbon has this same electron configuration, and so we have the overlap of those same types of orbitals, but 3 of those orbitals are used to make that triple bond, and then the last one here is used to make the sigma bond here between the carbon and here the hydrogen. Questions on that?
I have a question. So you said there's a sigma and 2 pi bonds, but you pointed out 2 sigma bonds.
What are we talking about? There's a sigma and 2 pi bonds in the triple bond.
Oh, okay.
Beyond the triple bond, there is another sigma bond. We have to make 4 bonds, right? So 2 of those bonds to this carbon are sigma bonds, right? A sigma to one side, a sigma to the other side. With that sigma, then we add in 2 more pi bonds. Now we've made a triple bond.
Thank you.
To make the alkyne, we have a sigma plus pi plus pi. But to make this single bond, all single bonds are sigma bonds. So we have another sigma bond. So we use this one to make another sigma bond, but in the other direction.
Okay, thank you.
Other questions? Okay, so looking at this, we have here, between these 2 carbons, we have 6 electrons, right, with this triple bond. So we end up with this area of high electron density, so that red area between these 2 carbons. Also, with this, because we have here in the middle face-to-face overlap, and then we have straight up and down overlap, and then we have coming towards you and away from you overlap, we end up with this cylindrical electron cloud. So you see over here, we end up with this pi electron cloud that's a cylinder around that triple bond. So we get kind of a cylinder. Everything's linear though. We get this cylinder of electron density there. And so you can see that here when we look at the electrostatic potential map. So we have our sigma bonds, we have our pi bonds. Which one's weaker? Remember, our pi bonds are weaker bonds, just like we said with the alkenes. Pi bonds are higher energy bonds, and so they are weaker bonds. Exactly what we said last chapter with the alkenes. So we end up with these 2 weak pi bonds that are going to allow us to do chemistry, and then we have this sigma bond. But remember, with sp hybridized carbons, it's going to be a linear shape. Linear. We can see that it is linear. So when we have a triple bond, it's going to be linear for the 2 atoms of the triple bond, and then whatever is directly attached to it. Whatever is directly attached to it. All right. Questions? Any other questions on this? All right, so with our triple bond, as I said, we have 6 electrons in a small space, but 4 of those are pi electrons. 4 pi electrons, but we have 2 more that are sigma electrons in a small space. So that means we get electron-electron repulsion, like charges repel. And so with that repulsion, that makes these alkynes very reactive. We can easily break those pi bonds, but when they react, it's usually going to be a very exothermic reaction. When alkynes react, it's usually very exothermic. So alkynes are super reactive. They can do polymerizations. We looked at polymerizations just with alkenes, but alkynes can do polymerizations very easily. And they can also do explosive decompositions. Here's one reaction that alkynes can do, combustion reaction. So remember, for combustion, you always use oxygen, and you make carbon dioxide water. plus some energy. What is that energy? Well, here it's the energy being produced. So we get a lot of energy being produced here in this reaction as we do this combustion. So here we're talking about acetylene. Remember we talked about acetylene torches. So you have this acetylene torch. You can heat it up to over 2,500 degrees Celsius and use that in welding. So you can go at high temperatures and you release a lot of energy as you're doing that. So you can heat up this acetylene gas to really high temperatures and use that in this welding process. So with our alkynes, let's think back to what we said with our alkenes. We looked at heats of hydrogenation and we said relative stability of alkenes can be deduced from how high or how low that heat of hydrogenation is. So we're going to do the same thing with the alkyne. So here we have a terminal alkyne, and here we have an internal. And we're doing a hydrogenation reaction. So we need 2 equivalents of hydrogen. Because we have 2 pi bonds we need to break. To turn an alkyne into an alkane, we need to break 2 pi bonds. We're doing the hydrogenation. So in this reaction, how much heat is produced? Well, for a terminal alkyne, more heat is produced than for an internal alkyne. So if we have more heat released, remember we're talking about everything getting to the same end where we have the alkane. And so we're seeing how much heat is released for one, how much heat is released for the other. More heat released is the less stable starting material. More heat, that tells you that it's less stable. So more heat is released when the terminal alkyne is hydrogenated. So that means that they are less stable than internal alkynes. So terminal alkynes are less stable than internal alkynes. Also, we can think about hyperconjugation. So internal alkyne, remember we have this that can donate in electron density. Here, this methyl, and then we have another methyl that can donate in electron density based on hyperconjugation. And so more alkyl groups, more stable. So stability of our alkynes. And it could be a different group on the other side, but we have our ethyne with no groups, then we add in a group, and then we have 2 groups on either side of the alkyne. That's going to be most stable. Questions there? All right, then let's think about acidity. So again, this is something we've talked about before. Acidity increases with greater S character. So how much S character does an sp3 hybridized carbon have? 25% S character. What about sp2? 33% S. What about sp? Now we're at 50%. We already said this before. I think we talked about this in like chapter 2 maybe. We said that between alkanes, alkenes, alkynes, alkynes are the most acidic. Because they have the most S character, the electrons are being pulled toward those carbons. So if we have these alkyne carbons that are pulling electron density away from the hydrogen bonded to them, that makes the hydrogen have a partial positive while the carbon has a partial negative, making this hydrogen acidic. And so we can add in some kind of a base that will deprotonate. It deprotonates, we end up with our conjugate base here and our conjugate acid. But here our alkynes are our most acidic of alkenes, alkanes, and alkynes. So we're pulling electron density slightly toward that alkyne carbon. So I can draw it in this way, away from the hydrogen. away from the hydrogen toward this carbon. Questions on that? So we're still talking about this acidity of our alkyne. If we have our alkyne and we add in a strong base, so what are our strong bases? Well, LDA is one, and you need to know the structure of LDA. If you're going to do a mechanism, you need to draw out LDA. And then another strong base that we're going to talk about that can be used to deprotonate alkynes is sodium amide. So it's NaNH2 in liquid ammonia. So we write liquid and then NH3 is ammonia. So what does this look like? Well, it's a sodium ion, and then we have a nitrogen with now two hydrogens on it. Instead of two isopropyls, two hydrogens. But whenever nitrogen has two bonds, it has two lone pairs, and so it ends up with a negative charge. Remember we said nitrogens with a negative charge are strong bases. So these are strong bases, and then we also said Grignard reagents are strong bases. All of these can be used to deprotonate an alkyne, but remember it has to be a terminal alkyne because there has to be a hydrogen there. So here, what are we using as a base? This base is N-butyl lithium, and we have diethyl ether as the solvent. N-butyl lithium. So butyl group with the lithium, we have an organolithium reagent. And so here we put in something that is acidic, right? Partial negative, partial positive. We're pulling electron density away from that hydrogen, what we just talked about. Alkynes are acidic terminal alkynes. And we have a strong base, partial negative, partial positive. So we can do an acid-base reaction. This is very reactive. And we form something more stable. Equilibrium lies on the side of the formation of the weaker acid. Here we get the weaker acid, which is just the alkane butane. And then we end up with your partial negative, partial positive. Now an alkynyl anion. An alkynyl anion. And we'll talk more about that next time. Questions here? All right, so that's our acid-base reaction with our alkyne. Some kind of a strong base added in to our alkyne. Because it's acidic, we can deprotonate. That's 13-2. Now we're gonna go into 13-3. So get out your IR NMR sheet really fast. Get out your IR NMR sheet. Remember we talked about how you need to have that with you in lab and have it with you in lecture. Basically just keep it with you at all times. All right, so the first thing we want to look at is that we already talked about our alkenes, and we said our alkenes are de-shielded. But look at where the hydrogens would show up that are directly attached to the alkyne. They're not as de-shielded. They're only found basically kind of close to where you would expect, just a regular CH, 1.4 to 1.7, just a little bit de-shielded, just a little bit up, downfield from where we would expect it. So it's close to alkane hydrogens, but we have our alkynes there. Remember, we also talked about this week in lab, aromatic, anything that is hydrogens attached to the benzene ring, right? But anyway, we have here an NMR. And so with this, we have our TMS. And remember we said our TMS, tetramethylsilane, shows up at 0. Then we have these 6 hydrogens. That's the integration, 6 hydrogens. There are 6 hydrogens that are equivalent to one another. They are going to show up here a little bit about 1. So close to 1 for those two, for those that a group of 6 hydrogens. Now notice here, it's getting split into a doublet because it has 1 hydrogen neighbor. And it's that blue hydrogen. Those 6 hydrogens have 1 hydrogen neighbor, which would be the blue hydrogen. So it's split into a doublet, but it's a 6 hydrogen doublet. That's the integration, 6H. All right, then we move a little bit further downfield. That's when we encounter the hydrogen of the alkyne. So the hydrogen of the alkyne, it's not far downfield, but here we see it. It's also split into a doublet. I'm going to put a question mark there because we're going to talk about in a couple slides why it's split into a doublet, because there are no hydrogens on this carbon. So why is it split into a doublet? But it's split into a doublet and it's a 1H doublet. And then we look at this blue hydrogen. This blue hydrogen has these 6 hydrogen neighbors. So it's split into a septet of doublets. Look at this here. We have 1, 2, 3, 4, 5, 6, and then teeny tiny down here, 7 doublets. So it's a septet, and then each of those peaks of the septet is split into a doublet. So it's a septet of doublets. So you know why it's a septet? Because of these 6 hydrogen neighbors. It's a doublet because of something else. We're going to see that the green hydrogen and the blue hydrogen can see each other. So that's why we see this extra coupling. But let's look at why this isn't far downfield. Why are these blue hydrogens further downfield? They're further downfield because, yeah, they're close to an electron withdrawing group, which is this alkyne. The alkyne is pulling away electron density, which is deshielding these blue hydrogens. But the green hydrogen that's actually on that carbon, it's not as deshielded. Why? Well, it's because of this. So we have these 4 pi electrons that are in that cylinder, right? We said it's that cylinder. And so what they do is we apply an external magnetic field. When we apply an external magnetic field, it forces those electrons, they start to move in a circle. So as they move in a circle, they begin to make their own magnetic field. So we get these pi electrons moving in a cylindrical area. And so as they do this, they're going to generate their own local magnetic field. And so as they generate their own local magnetic field, that magnetic field is going to oppose the external field in some areas, and it's going to strengthen the magnetic field in other areas. And so what's happening overall is that this local magnetic field that gets created is going to cause strong shielding. It's going to create a shield. And so we get this shielding effect that cancels the deshielding of there being these electron withdrawing sp groups. And so this hydrogen here isn't very far downfield. Because of the shielding from these pi electrons moving in a circle, they're creating a shield around that hydrogen. And so that hydrogen doesn't have a very far downfield chemical shift. So if you don't understand that, it's fine. Just remember that they're not going to be very far downfield because of this this local magnetic field that's being created here. So the next thing that we need to talk about here, though, is that we get this long-range coupling for alkynes. So you see this on your sheet. Look at your sheet. You see this listed there. So we get this long-range coupling. And so the long-range coupling is just 2 to 4 hertz, but it's between the hydrogen of a terminal alkyne and any hydrogens on the carbon 1, 2, 3 carbons away. 3 carbons away. So let's look at our spectrum here for this molecule. So again, we have our TMS, and then here 3 hydrogens. So these pink hydrogens, they have 2 hydrogen neighbors, so it's split into a triplet, and it's integrating for 3H. Then we move on to the black hydrogens. It's a 2H, but here it's a quartet of triplets. It's a quartet of triplets. 3 hydrogens on one side, 2 hydrogens on the other, quartet of triplets for these black hydrogens. Now let's look at green and blue in more detail. So for green, 1.94, 1H is the integration. It is a triplet, and the J value here is 2.5 hertz. This is for green. So looking at this, what would this building block piece look like? Well, this chemical shift is in the alkyne region. And so that tells me I have this carbon with a hydrogen that I'm going to label as 1.94. That's in a triple bond to another carbon. I know it's a triplet, and so here, 3 carbons away, I'm going to add in a CH2. And with that CH2, this is the long-range coupling where I get J equals 2.5 hertz. They're not right next to each other. They are 3 carbons away, but they can see each other with this long-range coupling. And so that's why it's split into a triplet. Let's do the next one, this blue one here. So for the blue one, 2.16, 2H integration, right? 2 hydrogens. And it is a doublet of triplets. And again, we see that same J value. If we see it one time, we see it another time. We're going to see that J value from 2 different directions. So here, 2 hydrogens, so I'm going to put CH2. And this is de-shielded. Why? Because it's beside the alkyne. This alkyne is pulling away electron density. So it's de-shielding these, so they show up at 2.16. Now 2.16, 2H, doublet of triplets. Well, triplet can't be over here on where this carbon is a triple bond. Triplet can only be over here. So there's another CH2. And then doublet, that would be this hydrogen. And so again, we see that J value from these hydrogens to this hydrogen on the end of the alkyne, which would be 2.5 hertz. So look at what this looks like. It looks like a doublet of triplets. It looks like a triplet that's split into doublets. This looks like a triplet. So we get this long-range coupling for alkynes. Questions on this? All right, then we have our carbon NMR. So turn your sheet over, look at carbon NMR. Alkenes, alkynes. Alkynes are not as de-shielded, right? Because of that movement, that cylindrical movement that those pi electrons can create, they will create a shield. And so alkenes are more de-shielded. So we see them at a higher value for the chemical shift. But here, obviously, the alkyne carbons are going to be more de-shielded than any of the alkane carbons that could be bonded to it. So you see these are high between 65 and 95 for any of the alkyne carbons. Lower value for, slightly lower value for the ones that are on the ends though. Questions on that?
Sorry, does de-shielding refer to the J value or the peaks?
De-shielding refers to where the peak is. So if the peak is at 0, that's upfield, that's shielded. The shield is electrons. De-shielding means there's something pulling away electrons. As things pull away electrons, then it gets moved further and further downfield. It's more de-shielded.
Got it. Thank you.
Dr. Navanian, regarding the J values, are they significantly any different than the alkenes that we saw last time?
What do you mean? Are the
So, like,
values themselves different?
Yeah, no, like, are the patterns kind of like the same? Like you have the Gemini and all that?
You can't have that, right? This is linear. So look at your sheet. There's only one possible value for alkynes.
Okay.
Because they're linear. All right, then our last thing is IR of alkynes. So if we have a terminal alkyne, we see 2 peaks. One peak is the CH of the alkyne, which we already talked about, right? 3,000, below 3,000 is alkane, above 3,000 alkene, a bit higher than that, alkyne, CHs. And then we also have this value for the alkyne carbon-carbon triple bond. Now, notice that they're showing you this in this way. This is really just for terminal alkynes, but it's still the carbon-carbon triple bond of the terminal alkyne. When it's an internal alkyne, then that carbon-carbon stretch is a bit too weak, so it's too small to see in general. So in general, we just look for, if you see these two peaks, you know you have a terminal alkyne. Usually if you have an internal alkyne, you're not going to see that carbon-carbon stretch. Questions there? What's the degree of unsaturation for an alkyne? Anybody put that in the chat. What's the degree of unsaturation for an alkyne? Exactly, 2. Why is it 2? Because it's 2 pi bonds, right? 2 pi bonds and 1 sigma bond. So if you see an alkyne, 2. Just count 2. You can look at a molecule. How many rings? Count the rings. How many double bonds? Count the double bonds. How many triple bonds? Count the triple bonds as 2 pi bonds. And so you just can count up. You don't have to do calculations. If you're looking at the molecule, you can look at it and know how many unsaturations it has. All right, any other questions? All right, we'll stop there. So I'm going to get your problem set graded, hopefully later today. I think so. And then you can view that over the weekend, and you have that to study. Remember, we will be having office hours next week, but everybody listening, for the Friday people, because your office hours will be after the exam, you can come to any office hour time earlier in the week if you would like to. So the office hour times, I believe, are listed on the syllabus, but if you need more specification, I think I'll post an announcement, but you're allowed to show up to any office hour time you'd like this week, just so that you can make sure you get your questions answered. And also, if you are nervous about your lab time, I think, when do we have office hours? I think you guys have office hours just Tuesday, Friday. So I don't think it matters. So everyone will have it on Tuesday. Yeah, I think you guys just have Tuesday, Friday. So if you want, you can show up on Tuesday to any of those times for the Friday people. Yes, we are having office hours today, and I will still meet for office hours next Friday, but I'm just saying, if you want to get some questions answered before the exam for the Friday people, you can show up earlier in the week. Now, I'll post an announcement with those times so you can see the times, but feel free to show up for the Friday people whenever. Any last minute questions?
Like a separate type of question I need to ask.
Like me privately?
Yeah.
Oh, okay. Well, then we'll wait for the people to leave. All right, you guys, have a good day. I love you guys. Have a good weekend. Be safe. I'll see you guys on Monday. Bye.
Thank you.